I would like to welcome you to lecture 5 of 2FH3. We'll continue in this lecture our discussion of vector calculus. We'll discuss a number of differential operators, the del operator and its application in calculating the gradient and divergence of vectors. And then we'll talk about divergence theorem and its importance. We covered chapter 3, pages 67 to 79. And we'll still have one more lecture to go in vector calculus, and then we'll be done by that time. At the start of the course, I explained to you that we have two forms for Maxwell equations. The first one is called an integral form, so all the expressions, all the relations between electric fields and scalar quantities are given by surface, line, and volume integrals, and we already covered this part. We covered the line integrals in different coordinates, the surface integrals and the spherical integrals, and surface and volume integrals. Now we need to cover the other operators used in the differential form of Maxwell equations. So one of the important operators that appear very often in electromagnetics and actually in all branches of science is the del operator. So the del operator, which is shown here, it simply asks you to differentiate relative to x in the x direction, differentiate relative to y in the y direction, differentiate relative to z in z direction. So the unit vectors ax and ay and az are not differentiated; they are constants. But you apply this operator to a scalar function. And this operator, you'll see it appearing in electromagnetics in three different forms. The first one is the gradient, which is this one here. And the gradient of a scalar function gives you a vector. So v here, the v that I put here is actually a function of x, y, and z. It's a scalar function. It's not a vector. But when you differentiate it relative to x in the x direction, differentiate relative to y in the y direction as shown here, differentiate relative to z in z direction, you get a vector e. We call this vector the gradient of v. And it has very interesting properties. We'll be talking about them in a second. The second use of the del operator that you will see very often is the divergence of a vector. And this divergence of a vector gives you a scalar, it gives you a number. So it takes a vector, and then the result of this divergence operator is a scalar. So here you differentiate the x component relative to x, plus the y component of the vector relative to y, plus the z component of a vector relative to z. And we'll see very soon the meaning of this divergence operator. It has very interesting meaning, and it's used in many applications in electromagnetics. The last form that I'm showing you here, this all in Cartesian coordinates, but of course in spherical and cylindrical they have completely different form. And you don't have to memorize that, you just have to keep them in your cheat sheets. So here we have the curl of a vector. The curl of a vector, it takes a vector, E, and it results in a vector as well. And as you can see here, it forms a determinant. The first row are the unit vectors ax, ay, and az. Second row are the derivatives. Third row are the component ex, ey, and ez. And the way we expand that, the way you expand the determinant, so you say it's ax multiplied by derivative of ez in the y relative to y, and derivative of ey relative to z. And then you repeat the same thing for all the other components. So these three operators, the gradient, the divergence, the curl, play a very important role in electromagnetics. You'll see them very often. They are related to certain properties of electric and magnetic fields, and you should know how to express them in Cartesian, cylindrical, and spherical coordinates. You don't have to memorize that, but just you should know how to use them. You can have the formulas, as I said, in sheets. I'm showing you here the del operator in other orthogonal coordinate systems. We talked about two other orthogonal coordinate systems, the cylindrical and the spherical. And this is how this operator looks like, and the book gives a derivation of how we can go from the definition of the del operator in Cartesian coordinates to its definition in cylindrical and spherical by using chain rule and by using mapping of unit vectors ax, ay, and az into a rho, a phi, and az for cylindrical coordinates, or ar, a theta, and a phi for spherical coordinates. I don't worry about these derivations too much. I just want you to read them and understand them for your own information. What I care about more is that when you have these expressions, you should know how to use them. So the first one means you differentiate relative to the to differentiate the component or the vector, or whatever, or the scalar relative to the root component, and this gives you a component in the root direction, and so on for all the other components here. One of the most important quantities that we use in electromagnetics and actually optimization as well is the gradient. So the gradient of a scalar function is given by this form here. So the gradient of a function v, which is function of x, y, and z, gives you three components. Gives you a vector which has three components: partial v, partial x. You differentiate v relative to x in the x direction, differentiate it relative to y in the y direction, differentiate it relative to z in z direction. So this gives you a vector with three components. This vector has many interesting properties. They are all coming from Taylor expansion. And here I'm trying to illustrate this for you in the figure to the left. I'm trying to illustrate this for you for a function of two variables. Because a function of two variables, when you have something like f of x1 and x2, this looks like a surface. When you try to plot the constant value contours, constant value surfaces, give you actually contours. So in other words, this is here the plane of x1 and x2. Every point here, this point here, say this point here, this point here, all these points have a value of 500 for the function f. So these are the contours, and it's a property of the gradient that it is always pointing normal to the constant value surface at that point. So for example, the gradient here, if you calculate it from the operator expression, you will see that its direction must be something like this. It's pointing normal. This angle here is 90 degrees. If you pick another point, say this point here, it must be normal in this direction. So the gradient does change direction from one point to the other, and it's if you pick a point, you want to calculate the gradient at that point, it must be normal to the constant value surface passing through that point. This is a very interesting property of the gradient, and I'm showing you here three other gradients in three other points. This point here, this point here, and this point here. This figure is taken from my book, Optimization. The gradient is very important in optimization, because optimization would like all the time to minimize some objective function. So would like to search in the negative gradient direction. Negative gradient will show you where the function decreases. So the gradient is always telling you where the function increases. So this direction here is telling you that this function increases in this direction, and this is the direction of maximum increase. So if at this point you try to go through any other direction, you see that the rate of increase is weaker. So it increases in a weaker pace along the distance. So the gradient is a very important concept. I'm showing you this figure here for two variables, but the problems we're going to be dealing with usually involves the potential V, as I explained here. And V represents usually a potential. It's a function of x, y, and z. In that case, the constant value surface is a three-dimensional surface, like an ellipsoid or a sphere or any closed surface in a 3D. And in that case, the gradient is a vector in this three-dimensional space. But for the example I'm showing you to the left, it's a very simple one, just illustrative. It's a function of two variables only, x1 and x2. But here in this case, the gradient has two components. In the general case we deal with, the gradient will have three components. One other thing to notice here is something called directional derivative. The directional derivative tells you how fast the function is changing, or what is the rate of change of the function in one direction. And how you get it, you dot product the gradient that you have by the unit vector. I made a mistake here and I intentionally kept it. So usually I don't use S, I should use AS, where AS is S over norm S, over the modulus of S. Okay, so the directional derivative is defined by a unit vector in the direction of S. Remember, if the gradient, so I can go back to that figure that we have here again. If I draw the gradient at this point, this is how the gradient looks like. If I pick any other direction S, this is S here. This is S, and this is the gradient. the angle between them is less than 90 degrees. So this is telling you that the direction S is a direction that the function increases along. So the function must be increasing in a lower pace than the one it would increase in the direction of the gradient. But if you pick some other direction, I will say this direction here, the angle between this direction and the gradient is more than 90. And when you do this dot product that I'm showing you here in this expression, you get a negative answer. So this is telling you the function does not increase along that direction, it actually decreases. So the gradient is a very important concept. When you it gives the direction of maximum function increase. It is normal to the constant value surfaces. And for function of two variables, the constant value surfaces looks like contours. We can draw them as in the figure. For the case that we deal with in this course, when you have a potential function of x, y, and z, it changes from x, y, and z. The constant value surface for the potential may be a sphere, it may be an ellipsoid, it may be any closed three-dimensional surface, and in that case, the gradient is a three-dimensional vector. You cannot really, it's not very easy to draw, and it's going to be normal to the constant value surface. Here I'm trying to, this figure is taken from the book. I'm trying to show you the general 3D case. So you have here, these are constant value surfaces, and these are 3D surfaces. They are not 2D. So each one of them has some, it looks like a 3D object. The volume enclosed actually a 3D volume. Okay, so the gradient at any point here in this space, you determine the direction of the normal, and this will be the direction of the gradient. Okay, this is the direction of gradient of V. You will know later in this course that when you want to calculate the electrostatic field, E, electric field strength at any point in space, you must calculate the negative of the scalar potential, scalar electric potential. So the scalar electric potential, once you find its a gradient with a negative sign, this gives you the direction of the electric field. A couple of examples on the electric in the way we calculate the gradient. So the first example is asking you to find the electric field given the scalar electric potential, and believe it or not, we'll be doing many of these examples later in the course. So here I have the expression for a potential in Cartesian coordinates. This is a potential here in spherical coordinates, and I want to calculate the electric field at these 2 points, 1, 1, and 0. And again, just remember, and this is something you will get used to it during the course, that the gradient, that the electric field is in the direction of the negative of the gradient. It's not the direction of the gradient, direction of the negative of the gradient. So once you find the gradient, you must multiply with a negative sign. So here in this expression, we simply go and apply the expression for the gradient in Cartesian coordinate systems and in spherical coordinate systems. So the function v in part A will be differentiated relative to x in the x direction, plus differentiated relative to y in the y direction, plus differentiated relative to z in z direction. And then once we get the gradient vector, we substitute for the given point B at 1, 1, and 0. For the spherical one, we use the expression of the gradient spherical coordinates. So this will give us, and maybe I should correct this one here. The R, of course, we use R as a small letter here in this course. So R is really the distance from the origin. We don't use capital R. Some books use capital R, but here it's small r. So this is the scalar potential is 2r cosine theta, and I would like to calculate the gradient. So we use the expression for the gradient spherical coordinate systems. Start our calculation. So the electric field, as you could see here, it is actually the negative. Here you can see the negative sign of the gradient. This is the gradient operator applied to the function v given. So what we do, we differentiate the function v relative to x in the x direction, relative to y in the y direction, relative to z in z direction. It's not a function of z, so the gradient will not have a z component. If you differentiate e to the minus x relative to x, you get minus e to the minus x. And this will cancel out with a negative sign outside, so you end up with this component. If you differentiate sine pi over 4, you get pi over 4 cosine pi over 4, and this gives you this term here. So this is an expression for the electric field at any point in space using this scalar potential. This is a voltage difference that we talk about in our electric circuits. If you want to calculate this at the point 1, 1, and 0, you put x equal to 1 here, put y equal to 1, and you put z equal to 0. So this will give you e to the minus 1 sine pi over 4. And this term here, this will give you e to the minus 1 cosine pi over 4. Sine pi over 4 and cosine pi over 4 are 1 over square root 2. So when you simplify, you end up with this vector here. So this vector here is square root 2 e to the minus 1. I took square root 2 out. I got this square root 2 by cancelling 2 with this 2 here with 1 over square root 2. So you end up with this vector here, and this will give you the direction, the magnitude and direction of the electric field at that point in Cartesian coordinates. To do the other part in spherical coordinates, we repeat exactly the same thing. We use the expression for the gradient in spherical coordinates, and again, you don't have to memorize that, just know how to use it. You should include it in your cheat sheets. So here the electric field is negative. Remember, this is negative, is coming from the definition of the electric field, and we'll be using this very often. It is equal to this minus gradient operator applied to the scalar function, which is 2r cosine theta. So what you do, you differentiate this potential V relative to r in the r direction. You differentiate it relative to theta, and then you divide it by r in the theta direction. You differentiate it relative to phi in the phi direction, and then divide by r sine theta. So if you do that, the derivative of this term relative to r will give you 2 cosine theta. The derivative of 2r cosine theta relative to r will give you 2 cosine theta with a negative sign, so you get minus 2 cosine theta ar in the r direction. Minus 2 cosine theta ar. If you differentiate the cosine theta, if you see the component of the gradient in the theta direction, if you differentiate the cosine relative to theta, you get minus sine theta. This r here will cancel out with this r here, so r will disappear. So this will give you minus 2 sine theta a theta. Now this vector can be simplified to minus 2az. Where this come from? It's very simple. If you remember, at any point in space, say this point here, this is x. This is the direction of x, y, and z. This is x. This is y, and this is z. And this is the r direction. If this is theta, this is az. This is here is a theta. Using very simple decomposition of the vector az, you can see we can decompose it into a component in the direction of r and a component in the direction of negative theta. And because this angle here is theta, this angle is theta like this one, so you get minus cosine theta. You get cosine theta ar minus plus the other one here in the theta direction. So this will give you here minus 2az. An example I want to show you is to find the directional derivative of the gradient of the function f of x and y is equal to xy squared plus 3z squared in the direction s equals ax plus 2ay plus 2az at the point 1, minus 1, and 1. So here, as we agreed, the directional derivative is a dot product between the gradient and a unit vector in the direction of the given vector s. So we have now to do two things. First, we get the gradient of this function in Cartesian coordinates. We calculate the gradient at the point 1, minus 1, and 1. And then we take the dot product between that gradient and the unit vector in the direction of s, which we call here as, which will be equal to s over the modulus of s. Of course, if this directional derivative is positive, this is simply saying that the function increases along s in the direction of s. If the direction derivative is negative, this means that the function decreases along s. This is a very simple function in Cartesian coordinates. So the gradient of the function is simply to get the gradient f, we apply the gradient operator here to the function f. So we differentiate relative to x in the x direction, differentiate relative to y in the y direction, differentiate relative to the z direction. The derivative of xy squared relative to x will give you y squared. The derivative of xy squared relative to y will give you 2xy. And because we had z as well, so you get here the derivative relative to z will give you 6z. So this is the gradient. We have the given point to us is 1, minus 1, and 1. So substitute for x to be equal to 1, y to be equal to minus 1, and z to be equal to 1, and you'll get this gradient at the point B. This is here the gradient at the point B is equal to ax minus 2ay plus 6az. Now, in order to calculate, this is normal. This gradient is normal to the constant value surface at this point, 1 minus 1 and 1. Now, in order to get the directional derivative at this point, we calculate the unit vector along the direction of S. You can see we divide S by modulus of S. And the modulus of S here is the x component squared, y component squared plus z component squared. Luckily, the numbers were cooperated, so this will give us square root of 9, which is 3. Then the unit vector is 1 over 3 ax plus 2 over 3 ay plus 2 over 3 az. What remains is simply take the dot product between the gradient that we had and this unit vector here to determine whether the function increases or decreases along the direction of S. So we do the dot product as shown here. This is, I simply put it in a more compact form. It doesn't really matter. This is the gradient at the point B. This is the unit vector along the direction S. Dot product will give you 1 over 3 minus 4 over 3 plus 12 over 3. And if you sum all this will give you here an answer of 3. Because the answer is positive, this is simply saying that if this was our gradient, this is the gradient here, then the direction S makes an angle less than 90 degrees with the gradient. So the function does increase along S. If the number was negative that we got, then the angle is actually greater than 90 and the function decreases along that line.